So thank you. I'll speak about slightly different problems to the most topics of this workshop. So I'll speak about image recognition methods and the problems of small sample size. It's a crucial problem in classification. So here is a quick outline of my talk. I'll give a short overview, I hope short overview. Then we speak about our approach to classification. Then we give several implementations of this approach, which demonstrates quite good performance. I don't think I will stop at our experimental results in details, but I'll have a very short slides. Then we give several applications developed for our approach, and give a brief conclusion, and I'll wait in questions at the end of my talk. So, okay, here is an introduction. It's a classical recognition problem. We have a set of cases, set of models, and we need to classify the query object. And the methods of the recognition methods usually depend on the structure of analyzed objects. So the most widely used approach is just represent an object as a feature vector and apply most of known classification methods. However, if the object become more complex, these methods, with pure implementation of these methods don't work. So there is some kind of group choice classification when you have a sample of identically distributed features, but it's not our case. And there is a sequence of segments which stands for difficult recognition difficult objects for recognition, for example, speech recognition or image recognition. It's a composite. We call them composite or piecewise regular object. Probably this model first appeared in speech analysis when the speech contains a number, the set of phonemes, yes, and one phoneme in fact doesn't depend on another. I mean, the features of one phoneme doesn't depend on the features of others, so you need to perform some segmentation to find these homogeneous parts, homogeneous segments, classify these segments, and unite everything in the whole hypothesis. Here is an example for image processing. It's actually the same, so we have short segments, and we compare them with the neighborhood of segments. It's similar to dynamic time warping of method in image recognition. So the classification methods depends on the properties of the available models database, it's for sure. And the most widely studied methods is the case when there are plenty of models per class. So, for example, the optical character recognition, when can collect a huge amount of images of the same digits. We can use plenty of machine learning techniques. However, the situation becomes quite different if we speak about small sample size problem. For example, one sample per model, so we have only one image for each class, so we need something else. And moreover, it depends on the number of classes in the database. So if the database is small, then practically any method can be implemented in real time. If the database is very large, then actually we speak about image retrieval methods. So we don't want to find the best. We want to find the best solution, but we understand that we can do this, so we need to find several appropriate solutions, yeah, with some kind of recall and so on and so forth. So here is a medium-sized database when we can speak about, in this case, it's an image recognition, yes. So we can trust to our methods, but we need to implement them in real time. And for these databases with complex classifiers, it's impossible, so we need to think how to improve the performance of these methods. Okay. Here is a small sample size problem. It's some very short classification. In fact, practically every approach can be viewed as a k-nearest neighbor search, because it's only one we can do here. One interesting way here is a binary classification of distances. So we check if two objects are homogeneous, so if they are from the same class or from other classes. In some cases, it can be implemented, in some tasks, it can be implemented very efficiently. For example, for now, it's a state-of-the-art approach, I believe, in face identification or face verification. So, okay, here is a conventional statistical approach for classification of these composite objects. We use a Bayesian rule. We use non-parametric estimates of densities, Gaussian Parsons kernel, and we apply the generalized, for this task, generalized classifier, probabilistic neural network. Here is the case. Here is a complete rule. Unfortunately, it's well known that in this case we test the simple hypothesis, so we believe that we knew each class, each density of each class. However, we don't know it for sure, so we need to estimate. We need to use some estimates, and it's well known that this solution is not optimal if we use even optimal estimates instead of unknown class densities. So actually, we don't have to reduce this task to simple hypothesis testing. We need to check the complex hypothesis. It's a complex hypothesis of homogeneity. So again, we need to test if the query object and each model object are homogeneous or not homogeneous. It's similar to Lehmann-Rosenblatt test, testing for homogeneity. We performed several calculations, and here is our homogeneity test in probabilistic neural network. It's some generalization of PNN from the previous slide. In fact, if the number of if the segment size, for example, the number of pixels in the segment is huge in the model database, then this expression is equivalent to conventional probabilistic neural network. Unfortunately, it doesn't work for complex projects, for complex tasks, because the computational efficiency is quite high. Actually, it's huge, because we need to compare every feature of every models in the database. So we have to deal with this for sure. We propose very simple scheme. We use only discrete features. So we describe each segment with its histogram and convert this to some known criterion. Here is a probabilistic neural network. In fact, it's some generalization of the Kalbeck-Leibler. I mean, minimum information discrimination principle. Here is our approach, and here is our approximation. Okay. So if we speak about images, we use several. The histograms of features are well known in image processing. It's either local descriptors or global descriptors. In our task, we concentrate on histograms of oriented gradients. It's pretty good method in image processing. And here is our grid. It's not it's not 16. Here is it's not 16 cells. We need much more. And here is our grid. So it's not regular grid. Here is the criterion. It's quite similar to this one. Okay. So fine. We have some classification criteria. We have experimental results, so it show that it's quite good. However, in fact, if the number of classes is large, the nearest neighbor rule also don't work. So what we do, how can we deal with this issue? We have several ideas. First of all, is to use so-called hierarchical methods. It's based on granular computer theory and sequential analysis. So we have several representations of the same object, and we try to analyze at first the coarsest level of granularity. It's very easy for speed. For performance. Then if the reliability is not enough in terms of choice reject option, then we proceed to analysis of the next level. And in fact, in each level, we also use sequential analysis if the distance, in fact, we have our rules is also some kind of nearest neighbor search. If the distance is less than a fixed threshold, we believe that we found a good solution. Here is another application. Here's another approach to deal with this issue at each level of granularity. It can be approximate nearest neighbor can be used here. And in fact, for our similarity measure, we can show that the distribution between two objects from different class or distribution of distance is non-central chi-square distance. It's well known from the maximum likelihood probabilistic density. So we use this to estimate probabilities and to perform the so-called maximal likelihood search of the next model to check. So we calculate several distances between previous objects, and we need to find the next model for which is the maximal likelihood in terms of our previously calculated distances. And we show that it can be implemented quite easy for our approach. It's a bit different method. I will speak about it very shortly because it's primarily applied for us in speech analysis. But in fact, it can be used only in video-based recognition when we use a fuzzy set theory and define each class as a fuzzy set of available models, of all available models, not only the models of this class, but all available models. So we define this fuzzy set based on the distances between models from these classes. So, and we can show that this approach is quite efficient if we have several frames containing the same object. So it's a video-based still-to-still recognition. Okay, experimental results. Very short. We have here we give some examples for face recognition, constrained face recognition with pretty old data sets. Here is our results for ferret data set. Okay, so the last is ours, so we can decrease the error rate. It's the same here, so in all our experiments we are pretty good. So here is examples of our approximate nearest neighbor search. It's a medium-sized database, so most of approximate nearest neighbor methods don't work pretty good. For example, a randomized KD tree. And here again we are quite good, especially for our distance. But even for Euclidean distance, the scale is not so good, but we have 2 or 3 times better case. So it's a parallel implementation, and I think it's interesting. It's for other search with quite large data set. Here is the brute force, and here is we. Okay, so here is sequential 3-way decisions. I told about it. It's hierarchical processing. Again, we have pretty good performance and quite appropriate accuracy right here. So finally, I will speak about short applications developed. Short developed applications. So first of all, it's our system for face recognition. It's constrained face recognition. It's still-to-still video-based recognition. Here is photo recognition. So we have some good results with this software. For now, we try to work with unconstrained face recognition. So when we don't use the histograms of oriented gradients, but we use some output of the deep neural network. But it's very preliminary stage, so I don't want to speak about it for now. Here is another application. It's called VZM recognition. So it's audio-visual recognition. When you see the video of a speaker and you try to recognize his speech. Okay, so recognize his speech. In fact, only wall phonemes and also pause phoneme can be recognized here. We use 2 kind of.
Language. For what language?
For Russian, sure. Yeah, we started it with Russian. Yeah. Everything is concentrated in our this research in Russian. So it's I don't know. It's 7 VZMs. It's one of my master students here. So she tried 2 kind of cameras. First is ordinary camera, and the second is Kinect camera. You know, Kinect and depth map camera. So it's here. And she created a pretty good application, and she showed that for Kinect depth map camera, unfortunately it's in Russian. Okay, but the error rate is quite good. So it's for our methods, and for conventional kind of camera, our performance is similar to known principal component analysis and so on and so forth. By the way, in in image recognition, the methods implemented, for example, in OpenCV don't show good quality. So it's.
Can you also recognize if she's happy or unhappy?
Yeah, emotion recognition is quite an interesting, I believe, solution.
We recognize it very fast.
Yeah, actually, we recognize the person very fast, you know. But
So imaging is still very primitive.
yeah, but I believe you need some video-based recognition, because in some cases you can't understand if the from photo if the person cries or he laughs, you know. For example, the same is for my kid. Okay, so here is the Kinect. It was interesting result because we showed that histograms of oriented gradients, our approach, worked even for this depth map camera. And final application is from machine vision. We have to develop a short application and show and understand if the cargo is available at some forklift truck, or is that sorry, here is the cargo and here is no, so we missed it. So we use some mathematical morphology and show that implemented an application of this image process and show that it's quite good and the performance is also appropriate for practical applications. Here is a very short conclusion. So we speak about small sample size. We understand that it's a really interesting and crucial problem, but it's a very difficult problem also. So we understand that the properties of classifiers depend on the number of models, so depend on the database, and we try to understand what kind of database, what kind of properties of the database influence the performance, the recognition rate. So we created several. We proposed several segment homogeneity approach, and this approach is quite is quite connected to maximal likelihood, to Bayesian statistics. So we succeeded in synthesizing several quite interesting methods and showed that they are suitable for practical application. So thank you for listening, and I expect questions, but I believe we have a lunch. So in fact, if we have a lunch, you can ask any questions to me. Okay.
Do you have any idea what is the connection between size of your, because small size, one is also small size, but you cannot recognize with only one sample.
What do you mean size?
Sample size.
You mean one photo for each person?
Yeah.
In fact, we can recognize it, but the quality is not so good. Here we go. For example, here is a case of only one photo per class. It's pretty simple data set, but even in this case, it's 10% error. So, but in fact, you can use any kind of even one class, even one photo, even one object per class is suitable for classification. But the quality is not sufficient, so we need to think something about some training. And as I said, for some tasks it's possible, because, for example, in face recognition, you don't have much faces of, for example, of you or someone else, but you can collect faces of other people and extract features of these faces needed to distinct. For example, I don't know, Brad Pitt from I don't know, from our some from Angelina Jolie or from Tom Cruise or something like this. So, and you can use these features to so you can build some feature selection method based, train this feature selection method based on this huge collection of photos. Then you can apply this, extract these features from your phrases and compare them. And in fact, in some cases, it works. So it's actually the same idea of homogeneity testing. So you test for homogeneity of two objects, query object and model object, but this homogeneity is based on some pre-training, based on extra data set. It's, I believe it's state of the art for now, so we try to find a way to to implement this with our methods.
It's amazing how the humans organize, because, for example, even now you are talking,
Yeah.
taking lots of pictures of you, go to my employee. But the issue is which one I selected, because I cannot store all of them. And then I can recognize you after.
Yeah, it's I understand. It's
Because the humans have a huge training set, and of course cannot keep all of them. But
Yeah,
which
sure.
one they selected.
Sure. But for now, what I know, for example, I last week I was at some seminar of one guy from St. Petersburg, who speak about this kind of physical understanding of what is doing in brain, some neural computing and so on and so forth. So they, for now, they use very simple models. Not model. Model is pretty good. It's like a physician model. It's I can't understand most of the notation even there. But they use very simple examples to understand the brain. So they don't, for sure, if I say to him, take a photo and analyze this, no. But they use only black and white images and some gradient orientation. So they understand that gradient is very important. So they try to, but their images are very simple. It's okay.
Just the beginning.
Yeah, I'm not sure that it's just the beginning because it's several decades, but it's very difficult. I say it's very challenging problem. So they try to understand it, and I don't know when we meet with each other.
So there are some approach with video recognition or no? With video, because we recognize video, I think.
Actually, we recognize not only video, we recognize 3D video. So it's two videos from two stereo pair. Yeah, we don't have a 3D video, but we have some small examples of video-based recognition. Yeah, it's something like similar to this, but it's an aggregation of. So it's so-called still-to-still image recognition. So you recognize one frame, other, and then combine them with each other. So it's some simple fusion, maybe, or something similar, or something more difficult. For example, with our fuzzy decoding method, we don't test it for video recognition. We test it for speech recognition. Speech is the same. It's a sample of frames, and you classify each frame and combine them with each other. Also, we tested it for artificially generated data sets. It's also very good, but for now, not for video based. So probably we have time for even for this. So, lunch? Thank you.